Hello everyone, and welcome to this instruction video in which we will build a very simple single server model in JamSim. JamSim is open source discrete event simulation software. And in this video, we make use of JamSim 2022 version 2. Once you open JamSim, you get the following screen that contains different windows. Let's go over them one by one. The most prominent window is the window in the middle. It's the largest one, and that's the view window. Here you get a graphical overview of the simulation model that you built. On the left-hand side, you first have the model builder. The model builder gives you access to a wide range of modules that you can drag and drop into the view window to build the simulation model. The object selector in the lower part of the screen gives you an overview of all the modules currently in your simulation model. Then in the lower part of the screen, we first have the input editor. This allows you to set the input parameters of the selected module, and the output viewer gives you an overview of some output parameters while running the simulation model. The system that we're going to build together is a very simple single server system, which means that it contains three elements: an arrival of entities in our system, a process that each of these entities goes through, and the entities leaving the system again. Now, as this is a quite simple simulation model, we actually don't really need the 3D environment over here. So let's turn it off and go to a 2D version of the view model. We can also turn off the axis and the grid in order to just have this blank window that we can work with. If you want to change the model title, you can do that by double-clicking the title and change it to anything you want. So let's make it a single server model. Let's go to the model builder and let's select the process flow folder, because here are all the modules that we currently need. The first module that we need is the simulation entity. In this module, we can set all the different parameters of a simulation entity. In this case, this will be a customer that enters our simulation system, and that wants to receive a service from an employee. So let's rename this entity to customer. For now, we don't really want to change the input parameters of this entity. The arrival of customers is modeled by the entity generator. So let's drag and drop the module entity generator in place. In order to receive the process, we will make use of an entity processor for the customers. So we can also put that already in the middle. And the module where the entities are leaving the simulation model, again, that would be the entity sync. Let's also give each of these modules a more appropriate name. So the entity generator, that will be customer arrivals. The entity processor, then, that would be the place where the customer receives the service. And let's focus a little bit on the visualization of the module over here. So you actually see that there are three components involved in this entity processor. You see the plus sign, you see the little wheel, and you see the minus sign. Now, each of these refer to an underlying process that will take place at this entity processor. The plus sign refers to seizing a resource from the environment. In order to receive the service, the customer will need an employee to be available. So the first thing to do is look for an employee that is currently available. Once the entity has seized the employee, it can receive the service, and that is depicted by the little wheel. Once the service is over, we go to the minus sign, where the resource, the employee in this case, will be released again into the environment, such that it can be used by another entity in the queue. So that's the entity processor. And then finally, the entity sync, that is where a customer leaves again. Now, for visualization purposes, I would like to add an entity conveyor between each of these modules, such that we really can see the entity moving from one module to another. So let's just add 2 entity conveyors over here, where the first one is arrival to service, and the second one brings the customer from the service to the sink. Now, another module that we need is a queue, because it could be that a customer arrives into the system, takes the conveyor in order to reach the process, and starts looking for an employee to get the service, but currently no employee is available. In that case, our entity, the customer, should wait in a queue. This is something that we need to model explicitly. So in order to do that, we will drag the queue into our simulation model. Then finally, we need to model the employee. And the employee, that's the resource in our system. And that's the only module that we cannot find in process flow. So we need to open the resource objects folder, and there we can grab the resource. Let's name it to employee. And as such, we have all the modules in place that represent the single server model that we are currently envisaging. Now, the next thing to do is tell JamSim what is the actual flow of our system. So what is the itinerary that an entity takes from its generation up to leaving the system again via the sink? There are 2 options to do that. First of all, you could go in each of these individual modules and manually change the value for the field next component, because that's the component that the entity would move towards once it leaves the current module. So if we're looking at the customer arrival, then the next component is going to be the module arrival to service, this conveyor belt that I installed. So I can manually select the arrival to service conveyor belt as the next component for the module customer arrival. If I now click the blue arrow on top, I would also see a visual representation of the connection between the customer arrival and the conveyor arrival to service. We can fasten the process by clicking the create entity links and then selecting any module in the system. We get access to that connection arrow automatically. And now we can just click the different modules in the order that they will also be visited by the entities in our simulation model. And as such, we implemented the flow of our simulation model into our JamSim model. Once we're done, we can unclick the button and we have the complete flow of our simulation system. Now let's go over each of these modules in order to set the right input parameters. Let's start with the customer arrivals. The field that we're interested here is the inter-arrival time. This is going to be the time between 2 consecutive arrivals of an entity customer in our model. Let's say that every 2 seconds, a customer arrives into our system. So we set the value to 2 space and then the unit, which is S for seconds. I could also use min for minutes or H for hours. 2 seconds in this case. So very consistently, every 2 seconds now, a customer is going to enter my system via the entity generator. Then the customer is going to travel over this conveyor belt. Let's make this just a 1 second travel time, just so that we have some visualization. For the queue, we actually don't really have to change something. We will just use the default queue, which is a first in, first out queue. People are patient. They will not run away there are no specific priorities and so on. So this is just a very standard first in, first out queue. Then let's look into the process. Here we have to scroll down to the last 4 fields in the input editor, where we're interested in the resources, the capacity, and the service time. So as this is an entity processor, we need to specify what are the resources that this customer needs in order to receive the service that it requires. In our case, this is an employee. So we need to open the resource list and we select all the resources that are needed for the service. In this case, we only have an employee. It's perfectly possible that in order to receive the service, you might need different types of resources, each with their own quantity. And that's something that you can specify now. So maybe you not only need an employee, but you also need a chair, you need an office to be available, you need an assistant to be there, you need 2 assistants to be there. So these are all things that you can set over here, right? So here you select all the types of resources that you need under the condition that you created these first, of course. And in the next line, the number of units, you're going to specify for each of the resource types how many units you actually need to seize from the resource in order to receive the service. In this case, we need 1 employee. So we can just put 1. The capacity then is the number of processes that can be executed in parallel. So in case that you have multiple employees, and in the case that they can work in parallel, meaning multiple entities can be served simultaneously, you want to set the capacity to the corresponding number of parallel lines that you have here. As we have only 1 employee, it's perfectly fine to leave the capacity equal to 1, as it's not feasible to have more than 1 service running simultaneously. Finally, we have to set the service time. And let's say that receiving the service requires only 1 second of time. It's important to make sure that the capacity of our system, in this case, well, 1 second of service time and 1 entity can be served simultaneously, that this is always lower than what you ask from the system. In this case, the customer arrival time inter-arrival time rather is 2 seconds. So every 2 seconds, a customer arrives, and a service takes only 1 second. If the service time would be larger than the inter-arrival time, or at least the service capacity would not be sufficient to process all the incoming customers, then just our queue is going to grow infinitely long, right? If a customer arrives every 2 seconds, but it takes 5 seconds to receive the service, then the queue is going to grow constantly. So we want to make sure that we have sufficient capacity in our system in order to be able to manage the inflow of entities over here. So 1 second of service time is definitely a good choice over here. Then we go to the entity conveyor. Let's again make that 1 second just to see the entity move from the entity processor to the sink. And at the sink, the customer is leaving the system again. There is nothing else that we need to set here. Let's quickly open the resource module. So the employee, here you might want to look into the capacity. And so that's exactly the number of resources of this particular type that you have available in the system. As we're talking about the single server model, of course, we only have a single server, so the capacity can stay equal to 1. So this is our very simple single server model. Before we try to run it, let's go into the object selector, scroll up, and let's select the simulation module, because this module allows you to set a few input parameters on the simulation in general. The parameters that we're currently interested in is, for example, the run duration. We're not interested in running the simulation for more than 8,700 hours. It's sufficient to just simulate the behavior of the system for 8 hours. We can set an initialization duration. It's some kind of warm-up period. if you don't want to start from an empty system, but for example, want to first run it for 1 hour and then only start the 8 hours of run duration such that the system already warmed up. Another thing that we will change is the print report parameter, which by default is set to false, but we want to make it true in order to have a little bit more insight in actually the results of our simulation model. That should be it. So we save the model. Let's save it on the desktop. And then we're good to go to run our simulation model. And we do that by pressing the play button. And once we do that, we see also a visualization of our simulation model. We can follow the clock over here. So you see consistently every 2 seconds, a customer is generated and arrives into the system. It takes 1 second to move into the queue, into the process, and then another second to move away from our system back into the environment. Okay, if you don't want to wait for 8 hours, which I completely understand, you can increase the speed of the simulation model by increasing this speed multiplicator as such. If you don't really care about these visualizations going on, you can also just unclick real time, and then the simulation will be executed in the background, and it's done almost instantly. So here you see that the simulation has completed 100% over here. We simulated 8 hours, and now we're interested, of course, in what are the simulation results. As in the simulation module, I set the print report parameter equal to true. I can now look for the report in the same folder as I saved my JamSim model. So let's look onto the desktop. And what I see, well, I have this single server.cfg file. That's my simulation model, but I also have now the single server.rep file. And you can open this file with any text editor, Notepad. I will use Notepad++. And what you see here is an overview of the performance of your simulation model split into the different modules that we actually instantiated in our simulation model. So first of all, we have some general information on the simulation itself. So you see that we run it for 8 hours. And now for each of the modules, we can get some statistical variables. Let's first look at the entity generator, the arrival of customers. You see that exactly 14,400 customers arrived into the system. And that's exactly what you would expect over an 8-hour time interval, knowing that every 2 seconds a customer arrives, right? This would mean 30 customers per minute times 60 minutes per hour times 8 hours would give you 14,400 entities. So this is perfectly as planned. What we also see, if we look into the entity processor, we see that all these entities started the service on the entity processor. However, not all the entities finished the service. So this means that at the end of the simulation run, the end of the 8 hours, there was still one entity in process. We see that the utilization is 50%, which is also exactly as expected, right? We have a customer arriving every 2 seconds, and the process takes exactly 1 second. So that kind of means that our server is working for 1 second and is then idle for another second. So in total, 50% of the time, the server is going to be idle in our system. And that's also what we see if we look at the resource module, where you see the units in use on average is 0.5. So 0.5 employees were in use on average. It's split into these different possibilities. So the number of hours that exactly 0 employees were in use, that was 4 hours. And the other 4 hours, exactly 1 employee was working. If we look into the queue, then we see that no queue was formed at all. So the queue length was equal to 0 for 8 hours. This is also as expected, as there is no variability in our model yet. We have an arrival every 2 seconds. We have a service that takes only 1 second, which means that if all the arrivals are very deterministic and are very well spread over the time horizon, there is no point in time when actually a queue is going to be formed. And that is what we see over here. Good. Let's look back into our simulation model and let's try to add a little bit variability here to make the instance a little bit more interesting. What we will play with is the customer inter-arrival times. So instead of making this very deterministic and constant 2-second inter-arrival time, we actually want this arrival time to be more stochastic. And we assume that the inter-arrival time now follows in exponential distribution with a mean equal to 2, but with a domain between 0 and plus infinity, right? So sometimes the inter-arrival times will be less than the 2 seconds. Sometimes the inter-arrival times will be more, but on average, we still have every 2 seconds an entity arriving in our system. We go to the model builder, we select probability distributions, and here we look for the exponential distribution. We add it to the model as a different module. We can also change its name. So let's make it the inter-arrival time of the customers. And then we can set the parameters of this exponential distribution. Now, the first thing that we have to change is the unit time. We have to tell JamSim what is the unit of the numbers that will come out of this probability distribution. In this case, we will represent inter-arrival times. So we will be talking about time units. Like this. We see that there are 3 parameters that we can set for the exponential distribution, which is the minimum value, the maximum value, and the mean. And as I explained before, we will not alter the minimum or maximum value, but we will set the mean to 2 seconds. So on average, the inter-arrival time is still 2 seconds, but there might be variation according to this exponential distribution. Now, if we click on the module customer arrival, we actually still see that the inter-arrival time is set deterministically equal to 2 seconds. So we need to change that. We need to remove this input. And instead of plugging in a number over here, we tell JamSim to look for the number that comes out of the inter-arrival time customers module. Like this. So this means that JamSim will use this probability distribution to generate numbers according to an exponential distribution with a mean equal to 2, and use these numbers as an input for the inter-arrival time for our generation process. Let's go back. So we reset the simulation and let's run it again in real time. And here you see that there starts to be some stochasticity in the inter-arrival times, right? So sometimes you see that these little balls follow quite fast after each other. Sometimes there is a little bit more time in between those. Let's unclick the real time in order to let the simulation run very fast in the background. And let's open our report again. So what do we observe? Well, first of all, we look at the arrivals, entity generator, and we see that actually only 14,392 entities have been generated. So that's a little bit less. It's very close, of course, to what we would expect in theory in a deterministic model. However, due to some stochasticity, we didn't reach the 14,400 exactly, but we're very close to the number. So that's as expected. Another important observation, if we now look at the queue, is that currently queues are formed. So just the fact that we installed the variability in the inter-arrival time, this actually caused uncertainty in the system, and this caused waiting times. We see that the length of the queue was between 0 entities and 7 entities. So up to 7 entities were queuing at a certain point in time. For each of the stages, of the queue, we can see how long the queue was in a certain stages. So we see that still the majority of the time, 6.6 out of 8 hours, there was no queue at all, and the system was working very efficiently. However, you see that there were points in time where the queue length was growing up to this not so long, right? It's only a few seconds, probably 2.16 times 10 to the power minus 4 hours. This is a time interval during which the length of the queue was actually equal to 7 entities. And you see that almost 1 hour, there was exactly 1 entity waiting in queue. If we would look at our resource, we again see that the number of units in use is approaching the 0.5 as we had before, but we again see a slight deviation. Okay, here we see that the deviation is lower. So we're slightly below the 0.5. This might be explained by the fact that we just have a few entities less in our simulation system now, right? So our server was only working for 0.49, so 49% of time, 49.9% of time. And so you see that actually a little bit over 4 hours our server was idle, so none of the employees were working, and a little below 4 hours, exactly 1 employee was working. Okay, let's go back to our simulation model and let's see what happens if we run the simulation again. So let's reset that. Let's run it again. Let's look at the report, and we see that nothing has changed. So despite the fact that our model is built on stochasticity, it's built on a probability distribution from which random numbers are drawn, we see that by running the simulation again, we get exactly the same numbers. That's not a mistake, but that is due to the fact that JamSim is generating the same random numbers over and over again. And this is, of course, not what we want, because what we now have is the simulation results for only 1 simulation run, meaning for 1 sample out of this probabilistic inter-arrival times. And if we would draw different numbers from that probability distribution, it's very likely that the behavior of our system will be slightly different. However, we cannot figure that out by just running the simulation again and again manually, because it turns out that we generate the same random numbers over and over again. Of course, we can fix that. And in order to fix that, let's select the simulation module. And let's go to the tab multiple runs. Because here you can set the number of replications equal to a value larger than 1. For example, let's run 10 replications of our simulation experiment. And actually, this change is going to do 2 things. So first of all, I'm no longer having to reset my simulation manually, but JamSim will do that automatically, running my simulation experiment 10 times in a row. But secondly, JamSim will make sure that the random numbers that are drawn from my probability distributions will be different during every simulation run. In other words, there will be a different seed for every replication of your simulation. So let's give that a try. So we increase the number of replications to 10. We're running the simulation model again, we see that now it takes a little bit longer, but still runs in a fraction of a second, of course. And we can look into the output file who did change right now. First of all, you see that the output file became way longer, as you now have the results of the 10 replications just underneath each other. So let's look at the first replication. The first replication is actually identical to the one we already discussed before. So you see the 14,392 entities arriving in our system. You see the utilization slightly under 0.5. You see the queue between 0 and 7 entities and 0.25 entities on average in queue, and the average queue time 1.4 times 10 to the power minus 4 hours. If we scroll down, we get access to the second replication of our simulation experiment, where we see that currently we find slightly different numbers, right? You see that the number of entities added is now slightly higher than the deterministic 14,400 entities that we had at first. So now 13 entities more were actually entering our system during the 8-hour time interval, which will have some consequences, of course. You see that the utilization, let's look at the process, right? So you see that the utilization of the process is now slightly above the 0.5. You see that my resource is actually working a little bit more than the 4 hours that it would work in a deterministic scenario. And you see that the queue lengths have increased even more, right? So now we have up to 9 entities waiting in queue. Why is that? Just because of the fact that there is variability, we were a little bit unlucky, you can say, in this simulation run by having generated inter-arrival times, which are sometimes slightly lower than the ones you would expect on average. And that means that slightly more entities have entered the system, so it was a little bit more busy than in a deterministic scenario. Let's look at the third replication to finalize this. Here we see that the number of entities is even higher. So we go almost 200 entities above what you would expect. This is perfectly normal, right? This is completely due to the fact that we have that underlying stochastic process. And do not forget that the domain of this exponential distribution is between 0 and plus infinity. So the deviation that we can have from the average value of 2 can be quite large. Let's look at the impact on our process. First of all, if we look at our resource, we see that, again, our server, our employee is working even a little bit more. We go towards 4.05 hours. The difference are very, very minor, right? But you see that the numbers are slightly higher. In terms of the queue length, we decrease a little bit. So there is one entity less as maximum queue length. However, if you remember the numbers quite well, you see that the average queue time increased a little bit, right? So that means that in the previous iteration run, there was probably one point where a lot of entities were generated very nearby each other, creating this longer queue at a certain point in time. Here, the queue was at its maximum level a little bit shorter, but overall, the queue was a little bit more busy. And so the waiting times were overall a little bit longer, not in the maximum case, but in the average case, right? So you see the queue length on average has increased slightly. And so you can start to analyze these results for all the different replications of your simulation experiment. And of course, you can start to do some statistical analysis over all the different simulation runs. Now let's make one final adjustment to our model. Let's turn our model into a multi-server model. So let me change the name of the model that I'm building. And let's save this as a multi-server model. Now assume that there is no longer only one employee available to provide the service, but two. There are actually two things that you have to change right now. Let me first reset our simulation. So the first thing that you have to change is you have to go into the resource module and you have to increase the capacity to be equal to the number of servers that you have of this particular type. So you have to increase the capacity to 2. But only making that change is not sufficient, because remember that in our entity processor, we also had something defined as capacity. And here the capacity referred to how many entities can be processed in parallel, how many entities can be processed simultaneously. So as long as this value is set equal to 1, it's not really helpful to have more employees, because we're restricting ourselves to the case where at most one employee can provide a service to a customer at a certain point in time. So we also have to increase this capacity and set it equal to 2 in order to make sure that, if necessary, the 2 employees can serve 2 different customers at the same time. If we now run the model again, we see that we have access to our multi-server report over here. So we can open that again with our Notepad editor. And let's just focus on the first replication over here, right? So in terms of the number of entities added, you see that we end up again exactly with the same number as we had in all our first replications, right? We didn't alter the arrival process of the customers, meaning in terms of inter-arrival times that were drawn from these probability distributions, we drew exactly the same numbers. So we have 14,392 entities arriving in our system in this 8-hour time interval. Let's focus on our resources. So you see that, well, there were times where none of the resources were working, but there were also times where 2 employees were actually in use, were working at the same time. Below, you can see how that is split up in time. So 4.76 hours of the 8 hours that we simulated, none of the employees was working. 2.5 hours, there was only one of the 2 doing something. And let's say around 45 minutes, so 0.76 hours, the 2 employees were working together simultaneously, both serving their own customer. And what is the effect on the queue length? Well, you see that the average queue length decreased quite drastically. We have at most 4 entities waiting in queue, but also the average queue time decreased quite significantly, right? So you see that most of the times that second employee was not really a useful addition to the model, but at these very specific times where it was a little bit more busy than expected, this second employee helped to reduce the waiting time of the system and make sure that the customers were served faster. So I hope that this was an insightful introduction into JamSim and in how to model a very simple single server and multi-server model. Hope you enjoyed the instruction video, and thanks a lot for listening. See you later. Bye-bye.